Section 7.3 is about independent and dependent events. So here are our goals for the day. So the first thing we're going to do is differentiate between independent and dependent events. And then after we've figured out what's what, we're going to calculate the probability of independent and dependent events. Starting off, let's talk about independent events. So events are independent if they don't affect each other. Oops, sorry. So they don't affect each other. So, for example, flipping a coin multiple times. If you flip a coin and it lands on tails, you can flip a coin and it can land on tails over and over and over. You're not like removing any options. Another thing that we're going to talk about, and this is an example we will use in a minute, is drawing a card from like a deck of cards and replacing it. And that's one thing I want to emphasize. So like if you take out the queen of diamonds, you put it back, you can draw the queen of diamonds again. And other examples, really most sports. We talked a little bit last section about like percentages and probabilities and whatnot, but like every shot that you take in basketball, every at-bat that you take in baseball, they're all independent events. Technically, they don't affect each other. You striking out the last at-bat, other than having a mental effect, isn't going to have much of an effect on your next at-bat. So the probability of independent events, if A and B are independent of each other, then the probability of A and B happening is just the probability of A happening, then the probability of B happening, multiplied by each other. So for example, we got a six-sided cube, aka a die, but this one's got some weird numbers. It's got numbers 1, 2, 2, 3, 3, 3. So 1, 1, 2, 2s, 3, 3s. The four sides, goodness gracious, are colored red, one side is colored white, and one side is colored yellow. We're asked to find the probability of each of these events. The first one is the probability of tossing a 2 and then another 2. So we're going to say the probability of a 2, then a 2 is going to be equal to the probability of rolling a 2 times the probability of rolling a 2 again. The probability of rolling a 2, that's 1/3. There's 2 out of the 6 options. That's 1/3. Same thing for the next one, 2 6 or 1/3. So when we multiply them together, we end up with 1/9. So you have a 1 in 9 chance that if you roll that die twice, you'll end up with 2 2s. The next one says probability of a red, then a white, then a yellow. So I'm going to say probability of red, then white, then a yellow. Sorry. That's just equal to the probability of a red times the probability of a white side landing up times the probability of a yellow side landing up. So there are 4 sides. That's 4/6 or 2/3 are red. There's only 1 out of the 6 sides that's white, and 1 out of the 6 sides that's yellow. So it's 2/3 times 1/6 times 1/6. Now for our numerator, we got 2 times 1 times 1, that's 2. In our denominator, we got 3 times 6 times 6. That adds up to a 108 when we multiply this together. We can reduce that, divide both those by 2, and we end up with 1/54. So there's a 1 out of 54 chance that that specific order will happen. Now, talking about coins, we mentioned that earlier. What's the probability of tossing a coin 3 times and having it land on heads, then a tails? This one seems complicated at first, but that's just the probability of flipping heads times the probability of flipping heads times the probability of flipping tails. Just because you flip 2 heads doesn't mean you can't flip another tails after that. So the probability of each of these is just 1/2 times 1/2 times 1/2, which gives us a grand total of 1/8. So there's a 1 in 8 chance. Now technically there's a 1 in 8 chance for every sequence. It could go heads, tails, heads. Won't make a difference.